Hey Phys 1 kids, Campbell here. In our first video on energy, we're going to talk about the different types of energy and how we can increase or decrease the energy of a system through doing work. Now, energy is defined as the ability of a system to do work, which may not really mean much to you right now. The great thing about using energy to solve problems like speed and height is that it's a scalar quantity, so we don't have to break things into x and y dimensions and then do vector sums. It just is what it is. The unit of energy is a joule, named after James Joule. It's symbolized with a capital J. Now, every system in nature has a total energy, and that's the sum of all the energies. There's all sorts of types of energies. There's kinetic, which is the energy of motion. There's gravitational potential, or spring, or thermal, or chemical energy. There's all sorts of energy. We're going to talk very briefly about them now. In class, I'm going to go into a little more detail. The first and very important is kinetic energy. Anytime you're moving, you have kinetic energy. Kinetic energy, symbolized by a K, is the energy of motion. There's gravitational potential energy, which is symbolized actually by a capital U, little g, and this is stored energy. And it's energy that's stored by putting an object at some height above some reference point. We usually use the ground as like the 0 point, but it could be really any point. There's elastic, or also called spring potential energy, which is a capital U sub S, and that's energy that we store in a spring, or like a rubber band. It's stored, and then when I let it go, we could give an object like kinetic energy. If I maybe put a little rock in here, or I just let it go and, oh, ouch, hits my finger. There's thermal energy, which is E little th, which is really energy inside an object. It's the sum of the kinetic and potential energies of molecules. Like in your body, you have thermal energy. There's chemical energy, which is energy that's stored in bonds, in chemical bonds. And of course, there's nuclear energy, which is stored in the mass of a nucleus. So anytime I destroy mass, because you actually can destroy mass, you get energy. Now, the types of energy we're going to focus on, these types are called mechanical energy. Mechanical energy. And we typically convert between these types of energy. Thermal energy is a type of energy that's important when there's friction involved. So we tend to lose energy to a system in terms of thermal energy. We won't really talk at all about chemical energy or nuclear energy in this unit. Now, there's the thing called energy transformations. Energy transformations is when I'm changing one type of energy into another type of energy. For example, I give this ball kinetic energy and I raise it up to some height, so now it has gravitational potential energy, and then I drop it, and that gravitational potential energy becomes kinetic energy. So that's a transformation. So for example, if you're doing weights and you lift a barbell, you're converting chemical energy in your body into gravitational potential energy of the barbell. Or if you're a diver, the elastic potential energy of a springboard, of that diving board, gets converted into kinetic energy as you go up, which then gets converted into gravitational potential energy until you reach maximum height, right? And then you get kinetic energy as you come back down. That's different from energy being transferred. An energy that is transferred means we are taking something from outside the system and putting it into the system. There are two ways to transfer energy into or out of a system. One is through work. Work is a mechanical transfer of energy to or from a system, and it's done by pushing or pulling. It's done by a force. So if I do work on a system, I can change the energy of that system. I can increase the energy. Or heat. Heat is another way. Heat is not temperature. Heat is the flow of thermal energy into or out of a system. Usually it's due to a temperature difference when I get this heat flow. But so I can increase or decrease the total energy in a system through an energy transfer, which would occur through like work or heat. Now, so like transformation is changing within the system. So it's like if I transform you from a frog into a prince. You've been transformed into this beautiful prince. Transfers is if I take you as the frog and I put you in the pond. So I move you. So that would be like a transfer versus a transformation. So transformation, I change within the system and the types of energy. Transfer is I am putting more energy into the system or taking it out. So work being one of those transfers. If I do work on an energy, I apply a force to a ball, like a shot put, I will give it kinetic energy. So I do work, I apply a force, and I give it kinetic energy. Striking a match, right? You apply a force to the match, and that does work. That gives the match thermal energy through friction. Slingshot shots, right? You pull back. So we do work, we apply a force to pull back this elastic band, and that gives it elastic potential energy. So this would be a transfer. Right now, this system has no energy. The elastic doesn't have any energy, but if I apply a force, I can transfer energy into the system of the rubber band. So work is energy that transfers into or out of a system. So if we look at a total energy equation, the change in energy is equal to the work that's done. And so we could be changing the kinetic energy, the gravitational potential energy, or the spring potential energy, any of these energies, if we do work. So work could increase the energy of the system. So if I, like the guy applying work through the shot put, applying a force and throwing it kinetic energy, that increases the energy in the system. But sometimes, like friction's a great way through work to take energy out of a system. So let's get into more detail about what is work. Work is done on a system by an external force. So those are forces outside of the system. Work is equal, from an equation standpoint, to force times the distance an object travels times the cosine of theta. And cosine of theta is the angle measured between the force and the displacement. And we'll look into a little more detail on that in a second. In order for work to be done, there has to be displacement. So if I just push in an object and the object doesn't move, I am not doing any work. Yeah, I'm applying a force. I can feel it in my muscles, but I'm not doing any work. There also has to be a component of the force in the direction of the displacement, or opposite of the direction of displacement. But it's very important to understand that not all forces do work, right? Pushing on an object and it's not moving, you're not doing any work. So let's take a look at the sign of work. It has to do with the direction, the force, the angle of the force to the angle of the displacement. So here I'm pushing a box, and the force I'm applying, that's the red arrow, is in the same direction of the displacement, which is that blue arrow. So they're in the same direction as displacement, so that means that this would be a positive value for work. When work is positive, that means that energy will increase. If we look at our second example here, so this example right here, the force now is not in the same direction as the displacement again, that blue line, but it has a component. So if I took the cosine of this force, there's my angle, right? The cosine would be the force that is in the direction of the displacement. So again, it's in the same direction. The component is in the same direction as displacement. So that makes work positive. And anytime work is positive, energy will increase. Now here, notice my force vector in this scenario here, my force vector is perpendicular to the displacement. That means, right, the cosine of 90 degrees is 0. So that means my work is 0. So perpendicular forces do no work. Perpendicular forces do no work. Very important. If we look at our last two scenarios, you can see that my force arrow is pointing in the opposite direction of the displacement, right? The displacement arrow is in this direction, and my force vectors are opposing that. So here it's at an angle, so the cosine of that, and here it's just opposite. So both of these cases mean that work is negative. A negative work value means that the energy of the system is decreasing. Remember, friction always opposes motion, so it always does negative work. So anytime there's friction, the work done by the frictional force will produce negative work. It takes energy out of the system, right? It would slow an object down, decrease its kinetic energy. What about forces that keep objects moving in a circle, in uniform circular motion? Do those forces do work? Absolutely not. That force is perpendicular to the direction of the displacement at any moment, any instant in time. So circular forces, or forces that are perpendicular to the direction of displacement, do no work. So not all forces do work. Let's do an example of a calculation. Here I have a strap. I'm pulling my bag with a strap. Interesting. And the tension of the strap is 20 newtons, and I'm pulling at a 45-degree angle. If I move that suitcase 10 meters at constant speed, how much work does the tension force do? Well, work is force times distance times the cosine of the angle the force vector makes to the displacement vector. So force is 20, the distance is 100 meters, and I'm going to take the cosine of 45 degrees. Make sure you're working in degrees and not radians. So if you do that math, you are going to get 1,414 joules. So I'm just going to two-significant figure that. And remember, the unit is joules. So that's how much work I did by pulling the suitcase. So this is the work done by the tension force. But what about other works? How much work does the normal force do? You know what? Let's draw a free body diagram. So there's my suitcase, right? There's my normal force. There's my force of gravity. There's my force of tension. And let's say there's friction, because, friction is always a thing. So if my object is moving in this direction, right, that's the direction of my displacement, our tension force is doing 1,400 joules of work. What about the normal force? Well, notice that the normal force is perpendicular. So there are very few instances where a normal force will actually do any work. So the normal force does zero work. What about the gravitational force? That does zero work too, right? The force of gravity is pointing straight down, but the object is moving on the horizontal axis. What about friction? Well, let's see. The work done by friction, right, would be the kinetic frictional force times the displacement times the cosine of theta. What's the kinetic frictional force going to be? I didn't give you any coefficients. I didn't give you the weight of the bag. I got a little clue here for you. What does it mean that it's going at constant speed about the forces? The sum of the forces are zero. So that means that the tension in the strap on the x-axis must equal the kinetic friction opposing it, right? So the force of tension, if the sum of the forces in the x equals zero, then the tension force in the x must equal the kinetic frictional force. Wow, interesting. Guess what? The work done by friction is the exact same amount as the work done by the strap. Interesting. If the sum of the work, so this actually means that the net work in this case is zero. And that if it's constant speed, then the speed of the object isn't moving, which means the kinetic energy is not changing, which means the net work is zero. That doesn't mean that the work there isn't work being done. It just means if I add up all the works, right? Oh, whoops, I forgot something. Negative work done by friction, that the net work is zero. All right, I want you to write a summary, fill out your WSQ, answer those questions, and we're going to talk some more about things like kinetic energy and gravitational potential energy in class. So I'll see you in class.